Greetings everyone, welcome to a pre-recorded version of my talk on multithreading and multiprocessing in Python, which I had at Python Guild at Gen a few days ago. So first of all, a few disclaimers. As is usual with my talks, I'm gonna show you a lot of examples, so we're gonna do a lot of coding. If you want to follow along or just want to try them out afterwards, you can check out the link in the description below where you can find the examples. And also in this talk, I'm not gonna cover asynchronous processing, namely async IO, because that would require a whole separate talk. But I will mention it briefly throughout the presentation. And I will also not talk about green threads, fibers, and so on. Basically anything that is scheduled by user space. So if you know like greenlet or eventlet, I won't be talking about those. And I also won't be talking about sub-interpreters, which is a hot topic in the Python world. Yeah. All right, let's start with some general terminology, so everyone is all on the same page. First of all, concurrency versus parallelism. If you take a look at an English dictionary, you will find out that these are usually used as synonyms, although in the IT world, these have two separate meanings. And I will illustrate it on this example. So let's say that we have two tasks, a blue task and a red task. And in sequential execution, what we do is we basically perform all the parts of the blue task, and then we can switch to the parts of the red task. If we are dealing with concurrent execution, we may start with a part of the blue task, then switch to a part of the red task, and so on and so on. So basically, this gives an appearance of simultaneous execution, although at the same time, we are only performing part of a single task. We never perform two actions at once. And performing two tasks simultaneously, this is what parallel execution is about. So in parallel execution, we may execute both tasks at exactly the same time. A program is basically your Python script, which is stored on the disk, or your Python application. When you run this Python script or application, a Python interpreter process is going to be launched. And this process has at least one thread, which is called the main thread. And threads are basically separate flows of execution, and you can have multiple threads per single process. And basically, in terms of operating systems and their scheduling, operating systems generally schedule threads, not processes. And as I said, these are like a flow of execution which are scheduled. Here is an example. It's more low level than you would imagine for Python. So for example, in Python, we do not deal with CPU registers. But this doesn't really matter, it's an illustrative one. So here we have a process where we have some code, we have some global data, and we have some open file descriptors. And then we have a thread which has its own stack, and in C or in like lower level programming, a separate set of registers. And now we can create a process which has many of those threads, so 3 threads in this example, and each thread is has its separate stack, and it has its separate like flow of execution, meaning that it can execute different instruction, different Python bytecode, and these threads cannot coexist in a single process. Now, another term that every Python programmer has most probably heard of is the global interpreter lock, the infamous global lock, that basically prevents multiple threads from executing Python bytecode simultaneously. And as I said, it's a global lock, which is locked when Python bytecode is being interpreted. and can be unlocked when there is another like action happening. Like for example, when a thread is waiting for an IO operation, like reading something from a disk or sending something to a network, the lock can be unlocked and another thread can run. And the purpose of the global interpreter lock is primarily to protect interpreter internals like reference counts, because not all Python interpreters are implemented in a thread-safe way, meaning that multiple threads can run in parallel. The global interpreter lock is in contrast with so-called free threading, which is a Python term for situation when the global interpreter lock doesn't have any effect. So for example, we'll see that in Python 3.13 you can build the interpreter with so-called free threading, meaning that there is no global interpreter lock. Here is an example. It's just a simplified version of what I'm gonna talk about, so bear this in mind. So for example, here we have a first thread which can run for some time period, and then it encounters an IO operation like writing some things to the disk. Then since this is on the kernel, like to do, it can release the global interpreter lock, and the second thread can acquire it, and it can run for a certain period of time, or in this case after stumbling upon an IO operation, in which case it repeats the situation with the global interpreter lock, repeats, and it can release the lock, acquire the lock, the other thread can run, and so on and so on. And these points here marked as IO, these do not necessarily need to be IO operations. It can be different like events that we're gonna talk about later. Okay, another two terms, cooperative versus preemptive multitasking. In this, the difference is whether the objects that are part of the multitasking have to cooperate together, or whether they do not necessarily need to cooperate and the Python interpreter or the operating system can take care of that. So in cooperative multitasking, here the primary example is async IO, where the tasks that are employed there need to cooperate together, basically need to relinquish their control in order for another task to run. And if you have a task that, or function that like hogs the CPU, then the other tasks cannot run because the CPU intensive task is basically blocking the whole event loop. In terms of preemptive multitasking, here this is something that, for example, threads use. They do not necessarily need to cooperate, and if there is a thread that is hogging the CPU, the interpreter or the operating system generally can preempt its execution and let some other thread or process or anything else run. So in terms of Python cooperative multitasking, this is something what async IO does, and preemptive multitasking, this is something how threads are implemented. So in terms of threads, they can either voluntarily release control, like for example, stumbling upon an IO operation, or the Python interpreter will pause them and let some other threads a chance to run. So there is no way for a single thread to hog the whole CPU for itself. And finally, two terms, thread safety and process safety. Basically, a function is thread safe if it can be invoked concurrently or in parallel by multiple threads without worrying about unexpected behavior or data corruption. And related term is process safety, which is basically the same thing but applied to processes. During the talk, we will mainly talk about thread safety, but note that there is a separate and related notion of process safety which applies to processes. All right, before we move forward, you can say that we are already 10 minutes in and we haven't seen any code, which is a cardinal sin, so let's remedy that. And let me fire up NeoVim and let me show you how to create threads, how to create processes, how to work those, just to give you an idea if you have never worked with them in Python. So first of all, to work with threads, we need to import the threading module. And now we can create it via the thread class, which we need to pass the target, which is a function that should be executed upon starting the thread. So let's create a foo function. And in that function, what we're gonna do, we're gonna just print the ID of the thread, just to see that it does something. Now, this creates the thread, but we also need to actually start its execution. So this method call will result in the thread being scheduled and this code being run. And then via the join method, we can wait until the thread executes its target function. So it will wait until it finishes. And if we run the code several times, we see that in each time we receive a different ID, which is expected because there is another thread created and running. If you want, you can also specify arguments in this way. So for example, here we can pass I like that. But of course you can specify anything else if you want. Okay, now the interesting part will come next, where we're gonna basically create several threads. So like this, range 5. And what we're gonna need to do, so for thread in thread start, and we need also to join each thread. So now if we run the code, we see that each thread got an associated ID. Instead of 1, we can pass that I here. So if you run it, we receive a different number. So that's an example of running several threads. One important aspect of threads is that they share, that you can directly share data between those. So if we create a global variable in this way and just set it to the ID of the thread here, and after its execution, we're gonna print that global number. We see that we got this value in the variable, which indicates that we were able to modify the variable inside the thread. Now, if you want to work with processes, you need to import the multiprocessing module. Now, in terms of getNativeID, we're gonna need to use the getBit function from the OS module. Similarly here. And in terms of threads, we're gonna use processes. This will be a process, right? And here we're gonna need to use the multiprocessing process function. So as you can see, the interface is very similar, although the most important difference is that processes do not directly share memory with each other. So if we run this example, we see that we got 0, which is the original value, even though we have overwritten it here, because right now we are in the main process and the value that is stored here is stored in child processes, and each of those has a separate copy of the memory. Yeah, so that's basically just a quick overview of how to work with threads and processes in Python. All right, now let me tell you some common misconceptions and myths, because I talk to a lot of people about Python and I also interview a lot of developers on Python positions. So I have heard quite a bit about Python, and not everything that people say is actually true. So I would like to cover this here. One misconception is that some people say that Python doesn't have threads, or that they cannot use threads in Python. as we saw, like Python really has threads. These are regular system level threads. It's nothing like user space, like green threads and so on. It's really system threads, and you actually can use threads in Python. Another common misconception is that that Python is single-threaded, or that Python is not multi-threaded. So Python is definitely multi-threaded. It's just not simultaneously multi-threaded, meaning that you can run several threads at once, but what you get usually is only the concurrent execution, not a parallel one, meaning that those threads most likely won't run at the exactly same time. Another thing that I hear quite often is that, hey, if you want to solve the global interpreter log issues, just use async IO, which is kind of strange if you think about it, because async IO runs only on a single thread in an event loop, unless you use a process pool or another thread pool. So in this case, if you run something only in a single thread, the global interpreter log is really, it's not an issue, but you only have a single thread. So async IO does not really solve any of the global interpreter issues. The global interpreter log in this case doesn't even like have any effect, basically. So that's just not true. Also, one common misconception is that since there is the global interpreter log, I basically do not need to use any logs and my code is still thread safe. This is not true, because the global interpreter log, it only protects the internals of the interpreter. And there are still some operations which are non-atomic, and you need to use locking or other synchronization in order for your program to be correct. So let me give you a quick example. So let's go back to when we had threading, which was this case. And what we are gonna do, we're gonna basically loop over 1 million times here, and we're gonna increment n by 1. We don't need this. Yeah, so we can drop that, and yeah, we're gonna create 10 threads doing that. And now here you would kind of assume that the value of n is equal to 10 million, right? Because we have 10 threads and each increases it by 1. What we're gonna also do, we're gonna import the OS module, and just to ensure that we can like reproduce it quickly, sorry. Where is it? Sorry, it's in the sys module. Yeah, we're gonna call this function, which defines after which time each thread is preemptively paused so that another thread can run. And the default value is 5 milliseconds, and we're gonna lower it to 1 millisecond so that the threads are switched more frequently. And also I'm gonna use PyPy here because it also makes the issue more apparent. So I'm gonna use PyPy and run test, and as we can see, every time we run this, we receive a different result. And if we want to find the reason, we're gonna import this module, and we're gonna disassembly the foo function like here. And here you can see that basically in the loop, what it does, it loads the global variable, loads the constant 1, then it performs the binary operation, and then it needs to store the value into the global variable. And what the global interpreter log only gives you is an atomicity of each of those operations. So the binary operation like itself is atomic, but not when like loading and storing the value of the global variable. So this means that multiple threads can override the value of the global variable. And in this case, you really need to use explicit locking, because the global interpreter lock doesn't save you. Another, I would say, misconception is that people cannot use threads for CPU-heavy computations. Like, nothing prevents you from doing that. Your program will still work, because threads are an example of preemptive multitasking, meaning that the Python interpreter will pause your thread after those 5 milliseconds, which is a configurable interval. So you won't hog the CPU for an infinite amount of time. And also, what is important to know is that the global interpreter lock can be released if the Python interpreter is not executing Python bytecode. So for example, if it is executing C code. So as an example, if you use the hashlib module for hashing or the zlib module for compression, each of those modules is implemented in C, meaning that the global interpreter lock can be released and you can have multiple threads in parallel performing hashing of some content. Or some C extensions like NumPy can release the global interpreter lock when doing some operations, so you can, for example, perform scientific computation in parallel, actually, even though it is CPU heavy. Another misconception is that people think that the global interpreter lock is really inherent part of the language, which is not true. Nothing in the language says that a Python interpreter needs to have the global interpreter lock. So yeah, and you can write your own interpreter if you are inclined so that doesn't have any global interpreter lock. And in the past there were some interpreters like IronPython or Jathan or for Python 2, which didn't have the global interpreter lock. Another point is that the global interpreter lock is not really specific to Python. There are actually other interpreters that employ the same strategy. For example, the MRI interpreter for Ruby, which is the reference C implementation for Ruby, also has the global interpreter lock. Another thing is that the global interpreter lock, actually the CPython interpreter doesn't have it, didn't have it from the beginning. And actually there were several attempts to remove it. The first attempt that I was able to find was around version 1.5, around 1996, where there was a patch of around 1000 lines that basically removed the global interpreter lock and replaced it with fine-grained locking, like around reference counts and so on. But the issue was that this was terribly slow for single-threaded applications, so it wasn't employed. And since then, there were several CPython forks that tried to get rid of the global interpreter lock. And one successful attempt we're gonna cover shortly. And the last thing that some people say is that Python sucks because of the global interpreter lock, to which I have two responses. Either that Python doesn't suck, or it sucks but not because of the global interpreter lock, but because of other things. But I would definitely say that it doesn't suck because of the global interpreter lock. Because, for example, we have ways of overcoming that by using multiple processes, or like even in Python 3.13 and later, there are really attempts to, completely get rid of the global interpreter lock from Python. Okay. Well, since the global interpreter lock is everyone's favorite topic, let's cover it and let's look at it more closely. So in order to understand it more, it's beneficial to know its origins, so that we are aware of the context in which it was created. And as you may recall, Python is fairly old. It's more than 30 years old now. It was developed during the late 1980s, early 1990s. And at that time, the major operating systems did not support threads as a concept. The support of threads was added only later, like during 1990s, like in terms of pthreads or Windows threads. And when this support came out in libraries, of course, Python developers wanted to use threads. But this posed a difficulty for the developers of the CPython interpreter because they wanted to allow people to use threads, but at the same time they knew that the interpreter was written in a thread unsafe way, and they would basically need to completely rewrite it in order to make it thread safe. So, because during the 1990s, I'm not sure how many of you were alive during that time. I was, and I can tell you that, like at least maybe in Europe, I'm not sure about the US, it was fairly impossible to find a multi-core or multi-CPU personal computer during that time. Like computers only had one CPU with one core. And so having a global interpreter log didn't make anything anything worse, because there was only a single CPU, so you were unable to achieve true parallelism anyway. So this was basically a good trade-off in that time. The difficulty came later when starting in the 2000s, like computers having multiple cores have started arriving, and then the global interpreter log became an issue when dealing with true parallel execution. So from the historical perspective, like the global interpreter log was a solution to an issue that people had during those 1990s. But it resulted in problems down the line. Of course, the global interpreter log itself has its benefits. So for example, it results in a simpler implementation of the interpreter. You just need to have one log basically and do not need to deal with fine-grained logging. And also another benefit is that single-threaded programs are faster because you only need to work with a single log and only lock it like when you start executing and unlock it when you are done. Of course, the drawbacks are that with threads, you generally don't have true parallelism, like simultaneous processing, apart from the cases that I have described. And also, basically, any Python developers need to be aware of it. People need to teach it, like I'm doing here. And basically, you need to be aware of that this is a thing in Python. Now, I'm sure that many of you have heard about the global interpreter log, but I'm not sure if many people have actually seen it. So let's take a look at it. Just a caveat, I'm going to show you a version of Python 2.6.18, which is the latest release of Python 2.7. And it's really old, and you can say, hey, Petr, why are you showing us this legacy, historic, ancient version of Python that nobody uses? The reason is that the implementation of the interpreter is simpler, and we don't have like enough time. I don't want to spend a long time like covering the Python 3 implementation, which is much more involved. So for educational purposes, it is okay to take a look at Python 2.7 because conceptually the global interpreter log in later versions of Python are similar. So we're gonna go to the Python directory, and here we're gonna take a look at the cevolc source code, which basically implements execution of Python bytecode. And the file has the usual shenanigans that you would expect, like a to-do list of things that have already been done. But yeah, let's go down. Let's go down here to line 238, where there is a helpful comment that this is the dreaded global interpreter log. And as you can see, even though you might not know C, this is a global interpreter. This is a global variable of this type, and there is just a single instance of this variable for the whole interpreter. If we go below here, we can see the initialization of threads. So basically, we create the global interpreter log and then immediately acquire it, so that anyone else who wants to execute Python bytecode needs to acquire the log down the line. Now, if we move even further, there is this function pyeval frame x, which is used for the actual execution of the Python bytecode. And yeah, there's a lot of code here. But if we arrive here, there is an infinite loop, which basically loops over each instruction in the code until we want to like stop executing that. And then here, if we are like working with threads, under some conditions, the interpreter will basically release the log so that other thread may run, and then we'll acquire the log back again. And yeah, of course, there are various issues with this approach, like whether the same thread is going to be scheduled or another thread is going to be scheduled, and fairness and so on. And that's just how things were implemented in Python 2.7. So just to give you an idea, and now you can actually say that you have seen the global interpreter log. Another important question is to discuss: when does the global interpreter log get released? And there are 4 situations in which it is released. The first one is when the thread stumbles upon an I/O operation, like reading or writing to the disk or communicating through the network and so on. So in this case, the global interpreter log is released while thread waits for kernel to provide the data and unblock it. Then in terms of the standard library, I have already told you that, for example, hashlib or the zlib module release the global interpreter log when performing the CPU heavy operation. The third situation is that when C extensions explicitly release the global interpreter log, like NumPy. And the last thing that we saw was that switch interval, which tells Python how much time can a thread run at most, and the default value is 5 milliseconds. And here we basically lower it to 1 millisecond. So as you can see, the interval is configurable if you are inclined to like do so. Okay, and finally, there's an important new thing in Python 3.13, which is experimental 3-threading support. By experimental, I mean that it's designated as an experimental feature by the developers, so you shouldn't rely on this in production, or I wouldn't rely on this in production. And also, if you want to use it, you will need to build CPython via a specific build flag that will disable the global interpreter log and make the build as special 3-threading build. Okay, so let me give you an example. I have shown this in my previous video about what is new in recent versions of Python. So feel free to check it out for more details, but I will just quickly go over that. So let's have a look. Here I have an example which creates, in this case, 12 threads and runs a terrible implementation of computing the Fibonacci numbers. By the way, don't do this. This implementation is terrible, but it is useful to illustrate the effect of the global interpreter log when the program runs with or without the global interpreter log. So if we run the program via the default Python implementation of Python 3.13, which contains the global interpreter log. I'm sorry, we need to see how much time it will need. So it should take a couple of seconds. Yeah, in this case, 6 seconds. And I also have a custom build of Python 3.14. You know, you can see here that's the experimental free threading build. So what we're gonna do, we're gonna run that experimental build. And here you can see that it only took like 1.8 seconds instead of those 6 seconds. So you can immediately see that the execution is faster. And this might improve over time when the devs work more on this no global interpreter log Python build. So I think the future is very bright and we should look forward to it. Let's take a closer look at how we can create, run, and terminate both threads and processes. So the first option is the manual one, which we have actually seen. It's via the thread and process classes, so I'm not going to repeat that. So we can start a thread or process, join it, and in terms of processes, we can terminate, like forcefully terminate those, although I don't recommend it unless you really know what you're doing. And you cannot terminate a thread because basically a thread doesn't have a chance to perform cleanup, like to release logs and so on, while a process can, although please beware even in terms of processes. And it is also possible to inherit from those classes and override the run method, although I'm not gonna cover that, so just be aware that this is an option. The second option, it's frequently used, and this is in case that you have some work which you can easily divide into separate tasks or batches, and you can create a process pool or a thread pool, like depending on the number of CPUs or cores that you have in your system, and let those processes or threads do the work. Let's switch back to here our example, and let's start. Let's start with processes. So we are gonna import the multiprocessing module. Now we're gonna need to create a process pool. So with multiprocessing pool, and we're gonna create a pool of 5 processes as pool. And here, what we're gonna want to do, we're gonna want to, for example, let's have a function foo, which accepts I, and it just returns, you know, a +1 version. Like, I don't know, this is not interesting, but it's educational. Now we can call map on the pool instance, which accepts the function, and then it accepts arguments. So let's pass it 10 numbers, and it will call that foo function with each argument in this process pool consisting of 5 processes. And now what we can do, we can iterate over those results, and then we can print each results like this. So again, the output is not really exciting, it's just the illustration. And of course here, if you are dealing with a process pool, you would do some CPU heavy work, like some computation. And if you want, there is also a way of creating a thread pool. In this way, you will just create a thread pool. The third option is via the concurrent futures module. This is a new way of doing things, or like new-ish, at least when compared to the multiprocessing module, which is fairly old. And the interface of the concurrent futures module is inspired by Java and its futures. So if you know Java, the interface is similar. And it's more compatible with other libraries, and the interface is simpler. So unless you know what you're doing or you don't want to think about it much, just use the concurrent futures interface. I'm more of a fan of the multiprocessing module, but yeah, I guess I'm an old schooler. So in this case, what we're gonna do is we're gonna import the concurrent futures module, and we're gonna create a process pool via this process pool executor, and the remainder is the same. But in this case, like underneath, we have futures. But if you just care about this very simple example, the interface is the same. And if you want to work with threads, you can create a thread pool executor. Now, in terms of the interface, here if you check the Python documentation, the pool class has a lot of methods, different maps, imap, star map, that you can employ, while the concurrent futures module, the executor basically has a way of submitting the execution of a single function, or that map method, which is similar to the one from multiprocessing. Yeah, and that's basically it. So the interface is really much simpler. Yeah, so these are the two executors. Now for processes, there are also other options. So let me just briefly cover two of them. The first of them is the subprocess module, which allows you to run other programs from Python. So here is a very simple example, which basically runs the ls command with the -l parameter. This tells Python to capture the output from the program so we can work with it in this case. And text equals true says to Python that, hey, please convert the output from bytes into a string. So we do not need to deal with that on our own. So in this way you can run the command and explore its outputs. If you want, you can go to a lower level representation, either via OS system, which is basically a way of running commands, although I don't recommend it. Or on POSIX systems, if you want to work with processes, you can use fork, which you might be familiar with from other languages, namely from C. And on all systems, including Windows, you can use the various spawn methods from the OS module to create processes. And now that we know how to work with processes and threads, let's see how to communicate basically between those or share data. In terms of threads, as we have seen, we can use the shared memory, like potentially with synchronization, unless the operations that you're doing are atomic. So I'm not going to repeat that. Another option is to use either the queue class or DEQ, which stands for double-ended queue, and it's a queue where you can append to both sides of the queue and work with both sides of the queue. In terms of the queue class, it's basically a multi-producer, multi-consumer FIFO queue, first in, first out. And let's see an example. I'm gonna here just show it to you. I'm not gonna create it from scratch because we would lose so much time. So here we create the queue. Here we create a worker thread. We specify this daemon flag, which says to Python that it doesn't need to wait until this thread finishes when it is supposed to end the program. And this is important in this case because we have a while true loop here, and we're gonna immediately start the thread. Now we're gonna put 20 items in the queue and wait until all the items in the queue are processed. The worker thread in a loop gets a task, just processes the task, and then signalizes to the queue that the task is done. This allows us to wait until the processing is finished. If you want, you can do it differently. You don't have to use this signaling. There are various options of utilizing the queue. In terms of processes, we have a multiprocessing equivalent for the queue class that you can use. Alternatively, there is this multiprocessing pipe class. It's similar to queue, although it is faster, and it only provides 2 endpoints, like for sending and receiving, and it has a limited buffer instead of the unlimited one in terms of queue. So let's just see a quick example. So here we create a multiprocessing pipe. This duplex argument, the default value is true, so you can omit it. But we have our 2 endpoints, and we can create one process with the first endpoint, the second process with the second endpoint, start above them and just join them. And now the first process is going to send the message while the second process is waiting to receive it. And after that, it waits for an answer from the second process, which is sent here. So basically, if we run it, we see that the second process first received the hello message and the first process received the hi message. So for some cases, this is good enough. We can work with shared memory with the multiprocessing module, although this will only give you access to C types compatible types. So for example, integers, arrays, but you will be unable to work with, for example, dictionaries in this way. So if you are fine with working with integers or like some primitive types and arrays, that this is what you can use. For other use cases, there's a way to create a server process via the multiprocessing manager class, which basically spawns server process, which is then used to as a proxy for those memory objects. And the benefit is that you can use pretty much any object you want, like for example a dictionary. And this also works when accessing the memory remotely, like from another process or even from another machine. It can be configured that way, although it is slower than using shared memory. So just to see an example, here we create the manager, and here we create basically a shared dictionary, which we then use in the multiprocessing pool, where we pass the dictionary as the first parameter. And in each process, what it does an in-place update of the dictionary. And here we can print the results. So if we run the code, we can see that we were actually able to modify the dictionary in place, which would be impossible if we were just using like raw shared memory in Python that we saw earlier. And of course, there are also generic approaches that work for both threads and processes. So for example, you can use files, like why not? Or you can use sockets, like network communication, even if your processes or threads are running on the same system, like why not, again? Or you can use pretty much anything that you are probably used to use, like databases or cloud buckets or Redis as cache, or some message brokers like RabbitMQ or Kafka or ZeroMQ, and pretty much anything that you can think of, like remote procedures calls like gRPC or Celery or like what have you. Okay, not everything is fine and dandy, and when working with threads or processes, there are multiple possible issues that you should be aware of. And let me practice that by saying that I would actually need a separate talk just to cover those in detail. So let me just give you a very quick overview of some of the issues. The first one, data races and race conditions. Some people treat those as synonyms, although they are technically different. Here is an example. So in terms of a data race, we have the same memory of this variable, and there need to be at least 2 threads when at least one of them is doing writing at the same time as other threads are reading the variable. So that's a data race. And a race condition in it, like the timing or order of events affects correctness. So for example, here one thread may read a variable, change it, then the second one reads it, changes it, and then both want to write it, and the write might happen at different times. So we are not dealing with the data race, but the order in which the writes are performed might affect the correctness of your code. So in this case, you might need to do locking in order for this whole block to be atomic. The second issue is blocking, and this happens when a thread is unable to proceed because it is waiting on resources to become available. So for example, it might be waiting for a log to be unlocked. A deadlock, that can be described as mutual blocking, meaning that two or more threads are basically waiting on each other and neither of them can proceed. Here is usual example that is presented. Let's say that we have two logs, 1 and 2, and two threads, A and B, and the first thread needs to acquire both logs, and thread B also needs to acquire both logs. But what can happen is that the first thread acquires the first log, the second thread acquires the second log, and now the first thread wants to acquire the second log, but this is already acquired by the second thread, and vice versa. So in this case, both threads are stuck and neither of them can continue. So as we can see, some issues can be resolved by using locks, but it's not a magic bullet, and some of the issues like blocking or deadlock might actually be caused by using locks. Another term is called lifelock. It's similar to deadlock, but in this case, the state of the threads constantly changes, but there is no meaningful progress. You can think about it as you are walking in a narrow hall and you want to pass someone who is walking towards you, and then you both step to the left to have a chance to provide a chance for the other one to continue, and then you both step to the right and both step to the left, and basically you are doing something. You are not completely stuck, although what you're doing doesn't result in any like meaningful progress. And in real life, you can basically use other channels like communicate with each other and so on. But in terms of our programs, this side channel might not be available. And finally, there's starvation. That happens when a thread is perpetually denied resources. So a thread is unable to perform its actions like for an extended period of time. I have already mentioned synchronization, like using locks and so on, so let's take a closer look at those. And the first note is that both threads and processes have the same synchronization primitives available, and I will just focus on threads just for simplicity. So the simplest synchronization resource is called a log, also called a mutex in other languages. It's a synchronization primitive that allows you to acquire log and then release a log. So let's see an example. If you recall our example with basically modifying the global variable, so here we have a similar one. And what we want to do, we need to ensure that we get to an expected number. So in order to make this atomic, we lock it or we utilize a log. Some of you can spot this inefficiency right away, but basically the locking is not free. It takes some time. So if we run the code like this, we see that it takes some time. So a better option in this case is to create a new variable like locun1 and then increment it, and then after we are done, we can add it while holding the log to n. And this approach is much faster than the previous one, as you can see from the timing. And by the way, it is recommended to use the with statement, the context manager, instead of doing like log acquire here and log release here. Even though in this case it doesn't really matter, because this shouldn't throw an exception. But just in case that you are doing something here that might be problematic and might raise an exception, it is better to use the with statement to ensure that the log is properly unlocked in case there is an exception. We can also have a so-called reentrant or recursive log, and this log can be logged multiple times via the same thread or process. So let's see an example. So let's say that we have a class that stores two attributes A and B, and then we create a log that is used for synchronization of access in order to make the methods thread safe. So we can change A while holding the log, we can change B while holding the log, and then we have a method that changes both A and B while holding the log. And the problem is if we run this code by using a log, it will actually get stuck, because here we lock it and here we want to here we want to lock it once again. So this can be used by using an error log, a recursive log, which allows the same process or thread to acquire a log multiple times. Then we have a semaphore. It's actually one of the oldest synchronization primitives, and it allows a selected number of threads to acquire it. So let's see an example. Here we create a semaphore which allows 4 threads to pass. Here we have a task, and in this task we try to acquire the semaphore, and we just print the current thread name and just like do some sleeping in order to see the output. And we create a thread pool and run it for 100 integers. So let me run it. Yeah, and here you can see I'm pressing enter so that you can see that the script is waiting. So every time there are only like four threads running, which is thanks to the semaphore. There is also condition, which is called a condition variable in other languages. I will skip it because it is more involved. And let's just take a look at an event, which allows us to wait until something happens, like until some condition becomes true. So here is an example. So here we create an event and 2 threads. And the first task does some processing and then signalizes to the second thread that it can start executing. And the second thread is waiting on the condition to become true, like on the event. And after the first thread signalizes it, the second thread starts running. So yeah, here we can see that we are processing, and then we are done processing, and then thread 2 can start. So you can use this for synchronization by waiting until a variable or a condition is true. And finally, we have a barrier, which allows a fixed number of threads to wait for each other. Here in this case, we create a barrier which waits for 5 threads to pass the barrier. Here we create the 5 threads, and each thread there is just random sleeping, just to better illustrate the effect. And each thread will get to this point where it will wait until all 5 threads reach this point, and then all threads will immediately pass the barrier. So if we run it, yeah, we can see that the threads are waiting at different times because there is that randomization. But what is important that as soon as the last thread wakes up, all the threads can pass the barrier right now. So it's a useful synchronization primitive. Yeah, and as I said, don't forget to utilize the with statement. Here I have tried creating a helpful table that illustrates the differences between threads and processes from various viewpoints. So in terms of the primary use case, threads are very useful for concurrent work, which is usually IO bound, like waiting for disk, waiting for network, while processes should be preferred when you are doing CPU intensive or CPU bound work, meaning you actually want to do things in parallel. In terms of the availability of shared memory, in terms of threads, you can use that memory directly because all threads share the same address space. But in terms of processes, you can only use shared memory like indirectly, not directly, as we saw like during that using that shared memory in the multiprocessing module implementation or multiprocessing manager. In terms of how much time does it does a thread or process need to be created and destroyed? Threads are more lightweight, so they are less expensive to create and destroy, while processes are more expensive because more things need to happen when you are creating a process, like the whole address space need to be copied. Even though you might be doing copy run write and so on, it's still more expensive. In terms of context switching, when different threads are or different processes are being switched or their execution is being switched, so it's easier to switch the context for a thread than of a process, which is similar to that create and destroy times. In terms of lifetime, threads depend on the parent process, so you cannot just kill the parent process and let the threads run. While processes are independent and you can like kill the child processes, kill the parents and so on, and it will still work. In terms of resilience, processes are more resilient because they are independent. While in threads, if you do something like stupid or you stumble upon an interpreter bug in the thread, the crash over one thread will basically bring the whole process down. So threads are less resilient. Only threads are subject to the global interpreted log. If you create a process pool, each process will have its own global interpreter log, and if you have just one thread per process, then GIL is not an issue. And finally, in terms of the estimated worker count, like in terms of threads, you could create like tens up to 1,000 threads and it will work like sufficiently quickly. But if you need to create many more threads, like 10,000s of threads, I suggest to use async IO, which is whose like primary use case is basically that, like having a lot of threads in quotes. In terms of processes, I have written here the number of cores, but with an asterisk, because this depends on what you are doing in the processes. If you are doing CPU heavy work, then I guess it doesn't make much sense to create more processes than you have cores, because then you are overloading your systems. But if you are using processes for IO operations as well, it might make sense to overdo it and create more cores or more processes than you have cores. All right, we are reaching the end, so let me conclude by giving you a few notes. I will not describe all of these notes in detail because I don't want this talk to be 2 hours long. So this is just something that you might want to look into by yourself. So just a rule of thumb, if you are unsure, just use threads for concurrency and processes for parallelism. I've described the difference between these two in the very beginning. In terms of achieving thread safety, there are additional ways, like from using synchronization locking to achieving thread safety. One of them is by avoiding shared state. And the two options that I'm listing here is TLS, which means thread local storage in this case, which is storage that is not shared among threads and that is specific to each thread. And you can also use immutable objects, meaning objects that cannot be modified, because if something cannot be modified, it is basically thread safe. Another important fact is that when writing multiprocess code, you can leverage the fact that if you write it well, you can run it on multiple machines. So you can distribute it and obtain more parallelism than you would be able by just using a single huge server. But yeah, this depends on the communication, and you need to communicate via means that are available in a distributed environment in this case. Daemon threads, this was the daemon parameter when creating threads. They are useful for background tasks like some monitoring, where you basically want to shut down those threads as soon as the main threads finish their execution. In terms of creating processes, there are two options. Like on some systems where fork is available, you can use it, like on POSIX systems, Linux, macOS. And on Windows, you can use just spawn, but you can use spawn also on POSIX systems. And there are differences between these two, which I'm not gonna go into now. Now you might be wondering what happens when there is an unhandled exception raised from a thread. In this case, the Python interpreter will call the except hook function from threading module, and it allows you to register code that should be run when an exception is raised. Another sometimes useful class from the threading module is timer, which allows you to run some code after the timer expires. So for example, you can set it to 1 minute, and after that 1 minute expires, certain piece of code will be automatically run in a separate thread. And finally, let me briefly cover the different use cases for threads versus processes, or threads and processes, not versus, but when you would use threads and processes. Like, of course, when you want to run multiple tasks, either concurrently or in parallel. If you want to achieve more resilience, so for example, the crash of a thread or an async IO task might bring down the whole program, but this might be fine in terms of processes. Another useful case is when you want to do some like background checks, background monitoring. This can be very easily done by using threads. And also, if you want to allow multiple things to happen in parallel, for example, if you are creating a program with a graphical user interface, you want that user interface to be available at all the time, even though you might be doing some CPU intensive work underneath. Okay, we have done it. So this is the end of my talk. Here I have listed some references that I suggest reading if you want to know more about the things that I have described. And I have also included this link to PEP 703, which is about the optional global interpreter log in CPython 3.13. And I've also included a YouTube playlist for talks about the global interpreter log. So if you want to, know more about the global interpreter log, feel free to watch those talks. All right, thanks everyone for your attention. Please let me know in the comments if you have any feedback towards my talk, and see you some next time. Bye bye.